The U.S. Geological Survey has turned to quantum technology to help it with the next generation of challenges in geological science. It established a Cooperative Research and Development Agreement, a CRADA, with a quantum company called Q-CTRL. For details of what's going on, we turn to the director of the USGS National Innovation Center, Jonathan Stock. Mr. Stock, good to have you with us.
Thank you very much, Tom. Pleasure to be here.
First of all, let's begin with what problems USGS has that you're trying to solve that quantum technologies will help. Then we'll get into what the quantum technologies are.
Let's bring your listeners in. Many of your listeners will be aware that we are in the middle of an energy transition, and we're moving into a future where we use electricity in different ways, and we want to store that electricity, and that takes minerals. And it turns out that the minerals we need to store our electricity in batteries, while that technology is constantly changing, and we may see new minerals come on, right now the minerals we need are in short supply and subject to disruption from, let's say, political events. So we have a national need to improve our ability to detect and assess those minerals in the subsurface.
All right. And so how do we do it now, and how would quantum technology help improve that?
So ideally, we would walk around with a large flashlight that would shine into the subsurface, and we would see the things we need. Sadly, that flashlight does not yet exist. And so instead, we depend on a host of geophysical techniques that are, in essence, ways of sounding the subsurface. For instance, some of my geophysical colleagues will fly gravimeters over Earth's surface and measure gravity. And the interesting thing about gravity is that although we're taught that it's 9.81 meters per second, it actually varies a great deal when you start moving out into those decimal places, right? And the reason it varies is because there are rocks of different density in the subsurface. So one of the tools that my geophysical colleagues have to map the subsurface is by measuring very precisely gravity. And when you move your gravimeter, which measures gravity, over a big dense body, the spring extends a bit more because gravity is a bit higher over that really dense body. It's attracting mass. And so if you're canny, you can fly your gravimeter around and measure variations in gravity that tells you something about what's in the subsurface.
Right, and it can tell by the reading whether it's lithium or iron?
Well, we're not that good yet, but it does tell us bulk density. And so one of the things that we try and do as geologists is we try and paint a picture of what the structure of the subsurface is. We use lots of different techniques. In this case, I'm focusing on gravity because it's, well, relative to the sensor that we're going to talk about, the quantum sensor. So we use gravity and we attempt to differentiate rock bodies in the subsurface. What does that mean? It means that we tell a big dense rock from a light rock. And so for viewers, for instance, granites are typically a relatively low density rock. That's the light stuff that often winds up in our countertops. Let's say a basalt or a gravel or a dark and dense rock. And so we can essentially tell where those rock bodies are on the subsurface. And then if we're really canny, it's guilt by association. We can look at the geometry of that rock body and say, well, this geometry suggests that this is a mineral deposit. And then we go to secondary tools to find exactly what kind of minerals are in that. So it's guilt by association, and it's about imaging that structure in the subsurface and improvements. And so the quantum part is a dramatic improvement.
All right. Yeah. So what is the quantum technology? I mean, you mentioned a spring. I guess that's a term of art, but there's something pulling down and then you get a readout.
That's the old school, like for those of us who suffered through physics classes in high school or maybe even college, right? You had a spring and you watch how that spring changes as it gets accelerated by, for instance, gravity. The modern day survey hires contractors who take very large gravimeters. These are sort of like, small Volkswagen-sized gravimeters. They fly them around in planes. It's very expensive. And we get a relative sense of what gravity looks like, and we can turn that into a subsurface map. Now, notice the challenges there. One of the challenges is it's really expensive, so we don't do a lot of it, or at least we don't do as much as we'd like. And the other challenge is it's really big, and so therefore we typically only do it over large areas. So the promise of quantum in this case is to shrink the size of that gravimeter, and also at the same time to either keep the accuracy or even in some cases, we hope, improve it. And so we're talking about taking an old instrument that's large and expensive and turning it into a much smaller, lighter weight instrument that's less costly. And that means that we get to shine our flashlight into the subsurface many more places with much higher resolution.
We're speaking with Jonathan Stock. He's director of the National Innovation Center at the U.S. Geological Survey. And the fact that you have a CRADA with this company that makes this quantum technology sounds like this is not something that's commonly commercially available then yet.
Not at all. And in fact, as the name implies, it's research, right? So we are working with Q-CTRL, and of course, we're interested in other partners as well to explore whether their software and sensors have the capability of getting us much lower cost, much higher resolution subsurface data. Of course, it's a CRADA, it's a Cooperative Research and Development Agreement. So, well, will it work? We don't know. It's research. We have a strong belief in this company and some of the others in the field that they have developed the tools that it takes to interpret this quantum data. And in fact, if you talk to them, they'll tell you that one of the ways they do that is they're essentially watching how atoms fall in Earth's gravitational field. So you've got this instrument, you're flying it around on a small platform. Maybe it's a drone, maybe it's an airplane. And then you're essentially watching how atoms fall inside the instrument, because the rate at which they fall tells you, well, the gravitational accelerant. Now imagine all the challenges to doing that while you're in motion. It's kind of like riding a unicycle and doing trigonometry at the same time, right? Because, the atoms are moving around not just because of Earth's gravitation, but also because, well, the plane is moving or the drone is moving. It's moving up, it's moving down, it's moving sideways, it's rolling. So all these different accelerations also influence. And then on top of that, there's the inherent noise that's in quantum techniques. And so the premise of Q-CTRL and other companies like that is that they can essentially do all the calculations that are required to remove that noise. So that's the trigonometry on a unicycle.
And what is the nature of the sensor that would be pointed down there that contains the atoms? And, just give us the big picture here. There's some atoms in it. What kinds of atoms are they, and what's looking at the atoms?
That's a great question. Q-CTRL, of course, are the experts here, but essentially we are shining lasers through these falling atoms and using diffraction patterns to tell us the rate at which particular atoms are falling. They have a variety of different elements that they use. And of course, there's a research industry built up around this. As you can imagine, the real challenge here is in taking all the noise out, because people have learned with some degree of confidence how to do this problem when we've got a big sort of Volkswagen-sized instrument sitting stable on Earth's surface, or relatively stable. The challenge is, okay, well, now what happens when you make it a lot smaller and start moving it around, right? And that's where all of the sort of trigonometry on a unicycle comes in, because you've got to take out all the accelerations from not being still and all the inherent noise in that quantum system. And for the details of that, that's a Q-CTRL question. They're good at
Sure.
that, and I wouldn't want to speak over them on that.
And with respect to just quantum measurement of Earth phenomena, besides gravitational fields, are there other things potentially that could be measured?
Yes, but we also have an interest in working with them on another geophysical measurement called magnetometry, which is essentially measuring the direction and strength of the magnetic field on Earth. And you can imagine, for similar reasons, if you have charged particles, they will orient. And once again, you can look at how those orientations happen at atomic levels and get, let's say, if you can get the noise out of the system, very accurate readings of direction and magnitude for the little magnetic compass that's sitting there in Earth's field.
Now, at the moment, you happen to be tasked to NASA. So is that because they think this could be useful and not just here on Earth?
Well, we do have an interest, and as part of that CRADA, we're exploring the potential to use these kind of low size, weight, and power sensors, in this case, gravimetry and magnetometry, or gravity and magnetics, to explore for resources off-world. As your listeners will know, if you can take small, lightweight things off-world that don't require a lot of energy, that's a lot better than taking really large, weighty things that require a lot of energy. So small size, weight, and power mean potentially we could develop maps of the subsurface of off-world bodies, whether that is the moon or Mars. And by doing so, find the things that I think the nation needs from us, which are, well, resources, batteries for a new economy, volatiles on the moon, as well as potentially hazards, faults in the subsurface, and let's say sources of volcanic unrest.
And just a quick question on the computing architecture of this. If you have some